Okay, the domain of the logarithmic function, if you remember, is all values greater than 0, right? So if I'm looking at any function involving a logarithm, we have to take that into account if we're trying to find the domain. So we're going to look at finding the domains of functions. Keep in mind we're going to have this new restriction, but we also have what? Restrictions where what? I'm either taking the square root of a negative number, right? I can't do that. That would be excluded from the domain. And I can't divide by 0, so any value of x that makes me divide by 0 I would exclude. Okay, so let's take a look at this first one. So here we have the function y equal log base 3 of 7 minus 4x. So this is inside the log function. Well, whatever is going inside the log function, whatever I'm taking the logarithm of, right, 7 minus 4x, right, the stuff in the parentheses, that stuff has to be what? Greater than 0. So when I talk about domain, then 7 minus 4x must be greater than 0. Right? So now we solve this linear inequality. How do we do that? We subtract 7 from both sides. 0 minus 7 is negative 7. And then I divide by negative 4, right, to get x here. But what happens when I divide by negative 4 to my inequality? You remember what happens? It changes direction, doesn't it? Whenever I multiply or divide by a negative quantity or linear inequality, it's going to change the direction. But negative divided by negative here is what? Positive 7/4, or 1.75. In interval notation, then, what is our domain? Everything less than 7/4 would be negative infinity up to 7/4. Do I do a bracket or a parentheses here? Parentheses, right? We want it to be strictly less than. We don't want to include 7/4. So there's the domain of this function. I can only plug in values of x that are less than 7/4. Okay. Let's look at the next one. Y equals log of x squared minus 9. Well, what do we have to have again? What we're plugging into the logarithm, which notice this is base 10. Again, for any base it doesn't matter. The domain will be the same. What we're plugging in this case x squared minus 9, must be greater than 0. So how do we solve this problem? Well, this is a nonlinear inequality. This is a polynomial inequality. Remember, we've been talking about those as well. So notice this thing here factors difference of squares. Right? And then what do we say? This polynomial is equal to 0 when what? X is what? When x is plus or minus 3. And so what do? We do a sign check, right? So we look at the sign of this x plus 3 times x minus 3. Sign of this thing. So I know at negative 3 and 3 it's 0. If I plug in something less than negative 3, like negative 4, then negative 4 plus 3 is negative 1. Negative 4 minus 3 is negative 7. Negative times negative gives me a positive. If I plug in 0, I get 3 times negative 3, I get negative 9. It's negative. And if I plug in something greater than 3, I'll get like 4. I get 7 times 1, positive times positive. I get a positive result. But you might recognize x squared minus 9 is a parabola opening upward. Right, just the parabola x squared shifted 9 units down. But there's the sign. And so what are we looking for now? We're looking for when x squared minus 9, or this factored expression, is what? Greater than 0. So it's greater than 0 where we see the positive quantities. Everything less than negative 3, everything greater than positive 3. Okay. So don't forget, so we can't just say x squared minus 9 is greater than 0, so x squared is greater than 9, and then say, well, therefore x is greater than 3. That's only half the picture, right? So x can actually be anything less than or equal to negative 3 as well. That will make x squared minus 9 positive, making that in the domain of the function. Alright, what about this one? This looks pretty simple. Just natural log of x down here. Well, right off the bat, what do I know? Natural log of x, I know that x must be what? Greater than 0, because what I'm plugging into the log function has to be greater than 0. But there's something else. Since I'm dividing by the natural log of x, the natural log of x itself cannot be 0. I can't divide by 0. 1 divided by 0 is undefined. Well, when is the natural log of x equal to 0? What's the natural log of x again? It's the exponent on the base. What's the base here, by the way? What is ln? There's no, what's the base? The base is e. Do you remember from the last video? This is base e, right? And so, if the power is 0, right, on the base, what is e to the 0? What is e to the 0 power? That is 1, right? So that means that my x cannot be 1, right? Because if my x was 1, the natural log of 1 would be 0, right? Natural log of 1 is equal to 0. And so this information tells me what? The value of x is positive, but it can't be 1. So it's everything greater than 0, but I have to exclude 1. So I go up to 1, exclude it, right? Parentheses, not bracket. And then my union, what? Everything greater than 1 would be 1 to infinity. So there's the domain. Basically everything excluding 1. Okay? So really important to see how that affects the domain when we're dealing with logarithmic functions. We have to keep that in mind, that the input to the log function must be greater than 0. Okay, let's look at a little application involving logarithmic functions. So here's a modeling problem. We have that students in a psychology class took a final exam, and as part of the experiment to see how much course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. Sounds like a lot of fun, right? You take a final exam and then you take it again a month later, and then a month later, and a month later. That'd be a lot of fun. I'm sure they had to pay those students to take part in that. But the average score for the group after T months was modeled by this. Okay, so T is the number of months. Okay, so what was the average score for the original exam? Well, the original exam, when was it given? How many months after the original exam was that given? You say, what? That doesn't make any sense. It was given at the same time, and so T is what? 0, right? I mean, the number of months after the original exam was given was 0 months. So initially, right? Initially, this will tell us what the average is. So if I plug in T as 0, what do I get for T? I get 0 plus 1. Just plug it in there. So this becomes what? The natural log of 1. But what is the natural log of 1? What is the power on the base e needed to get 1? E to what power is 1? Answer, 0. In fact, that's always true. Log base anything of 1 is always 0. This is, again, log base e. So the answer is 88. So the average was 88, right? 15 times 0. 88 minus 0 is 88. So initially it's 88. And notice as t gets bigger, then this quantity here is going to change from being 0 initially, right, to a bigger and bigger number. And what's going to happen to the average? It's going to go down, which kind of makes sense, right? Over time, as you take it, you begin to lose, you forget things, right, unless you keep doing it. So on average, the test score will tend to go down usually, and that's what's happening. Even though they studied hard for that final exam, afterwards they're going to begin to lose the material and forget some of it. Now, what was the average after 2 months? Well, 2 months after, t is the number of months after, so t is 2. And so what is f of 2? Going into the original equation, it's 88 minus 15, natural log of what? 2 plus 1, natural log of 3. Okay? Now, I don't know what the natural log of 3 is, like I knew what the natural log of 1 is. It's the power of e needed to get 3. E to some power is 3. That's what this is. I don't know what that is, but I can approximate everything with our natural log button. If you remember, we have that natural log button right next to the 4. So let's do this. 88 minus 15 times, let me turn the calculator on. Okay, let's try that again. 88 minus 15 times the natural log of 3. All right, so that's exactly what we have here, and we approximate that, and we get about a 71.5. We'll round that off to 71.5. So notice the average has gone down from an 88 average now, 88% I guess, 71.5%, so it's gone down. What about 1 year later? 1 year later, oh goodness, how much do they remember? Well, what's t in this case? Remember, t is the number of months afterwards, so 1 year later is what? 12 months. So what is f of 12? What's the average there? It was 88 minus 15. What log of what? T is 12. 12 plus 1, 13. Okay. So I'm just going to edit. Show you another quick trick. I don't know if anyone knows. If you're doing things, if you use this entry button, look at second, and then hit entry, look what it does. It recopies what I just printed. And now you can move these arrows around and you can edit this expression. I can edit this 3. I'm going to insert second INS, insert. So that's now got an underscore, meaning when I type it will shift things over. So there's my 13. And now I can evaluate. So some of you might know already how to do that, but there it is. And notice our average. Oh my goodness, we've gone down to 49.5%. So after a year, the average is a failing grade, right? So hopefully with your algebra skills and later as you learn trigonometry, you will not lose them, because if you go on to calculus, you will be using them. And so we want to make sure you retain the information that you're learning in this class and the next before you go to calculus. Okay, so what we're going to look at in the next lecture will be some properties of logarithms. And logarithms being exponents, we know something about them, and we have some interesting properties, very useful properties, that we're going to explore in the next lecture.